Okay, welcome everyone. We're up and running. So this is going to be a little bit of information about 5.3. Um, we'll call it interpretations of the integral. Okay, so let's say you have some function, doesn't matter, bloop, goes from A to B, an interval, okay? And then we have an axis, looks like this. Oh, that's funky. That's crazy. Okay, so keep in mind that if we have a little slice of this, and it looks like it is somewhere in here, that this slice has some infinitesimally small width that we talk about as delta x or dx in Leibnizian notation. And then because this is also has a height, what do we call the height of this rectangle? Here's the y-axis. No, not dy dx, just the height of this. Y is closer. Uh, it's related to this. No, this is x. Think old school. The height of anything. Close to y, but in function notation of, there you go. So the height of this is f of x, okay? So if we want to express the area of the rectangle, then would be what? F of x dx times dx. Good. And then if we want the sum of the areas, sum of all rectangles, we would say that's the integral sign from A to B of f of x, the height, times d of x, that infinitesimal, tiny little width, because that's an area. Height times width, and the integral sign, remember, developed from the sum sign, sigma, so this is the sum from here to here of adding up all these little tiny rectangles, okay? And there's a bunch of them, there's a bunch of them. Whole bunch of them, you sleepy people. And I won't talk too long because I know it's hard to listen when you're sleepy, but this is important stuff. So we're adding up all these tiny little slices. And this is an ongoing theme that we'll see throughout integral calculus. We're just adding up, we're summing them. And let's come up with some proper terminology now. So we've talked about the integral sign. Integral sign. S-I-G-N. No. Psi. The integral psi. So we have the integral sign there. We have the lower limit of integration. All right, you guys, pretend to be paying attention. Lower limit of integration. Guess what B would be called? Oh, I can't get anything past you. Upper limit of integration. Okay, B, upper limit of integration. F of x is called the integrand. That might be a new term for you. Integrand with a D. And d of x, the last one, is the variable of integration. Okay? Nice. And with the whole thing, we say the integral from A to B, or that interval. And basically you're saying we're just adding up all the little width times height, all the little areas, we're just going to add them up over that whole interval. Okay? Questions, worries? It's okay? So then there's one other concept. If let's do something a little bit more specific. So it's cold out there now, and there was an example in the book kind of like this, and I thought they should have run with it a little bit more. The one about the cost of heating, time in days, the cost of heating your house with respect to time. Um, let's say this is January 1st could be day 0, and then out here day 90 would be approximately when? January, February, March, April 1st-ish, because February's short, about April Fool's Day. And where did that come from, you literary types? I wonder where that started from. But anyway, day 90 would be about then. And this year is pretty, it's a different year in terms of it's kind of warm. But in general, what would this function look like in general? Yeah, Hannah. It would do what? Decrease. In general, it's cooler January 1st, and it would have some bumps, you know. But in general, it would decrease because it gets a little bit warmer into March. You track athletes are glad for that, right? And because it's decreasing, that means your cost is decreasing. So this is cost of heating your house, and this is in dollars, US dollars. Okay, so we can say then that, and we have our interval, let's put that in. Let's write a statement about this cost of heating your house. Okay, what would this be? Derica, I'm going to pick on you. Mm-hmm. Well, tell me what part you do know. Don't try to do it all at once. Do it a little bit at a time. Salud. The integral, good. 0 to 90, perfect. That's the lower limit and upper limit of integration. You're on a roll. Okay, good. Really good. And then remember, we're going to have a bunch of little rectangles here that have some width. Oh, it wouldn't be dx this time, would it? What would it be? Dt, because it's a derivative with respect to time. Okay, delta t. Okay, and then what else would we have? Wouldn't be f of x in this case. What would we call it? How about c of, then what's our variable going to be? T, there you go. So we're saying this is the cost of heating the house with respect to time. Okay? So then what goes up here, Jericho? We're almost done. Home stretch. C of t times d of t. Good, because that's the height times the width, the infinitesimally thin width of that puppy. Okay? Boom! That gives us the total cost. Okay? For total cost. And that's represented by area under the curve from 0 to 90 of this function. Okay, let's think about that in terms of units. Okay? Let me clone this. Let's think about it in terms of units because this is important. First, I better group it. Then I better clone it. Okay, so I'm going to bring this down here so we have a little more room to write. So we said the cost was in dollars, the time is in days. So we're doing dollars per day times days, right? Equals, equals dollars, yeah. And I think I goofed that up a little bit because this out here would be dollars per day. I think I didn't include that. This would be dollars per day. Yes. And then we would go dollars per day times days. And units are really important here to help you keep this straight. Those divide out and you get dollars. And that's what we wanted because it's cost. Okay? So that's pretty cool. And then your book introduced one new concept that they kind of went fast on it. Okay? As I said, total cost would be this, just adding up the total areas. But if you wanted the average cost per day, because obviously it starts out high and gets lower, they kind of glossed over this. The total cost would be everything added up from 0 to 90. Think of what the average cost of this would represent. The average cost. Well, think of it like this. Think of it like this, and those are some good suggestions. The highest cost would be one of these days out here, somewhere in January, right, on a cold day. And the lowest cost would be out here somewhere on the warmest day, right? The average cost of heating would represent what in terms of these areas here? Think of it like that. Pardon me? The average of the areas, yeah. And if you just took the total cost and thought of this as like, if this is the tallest or the biggest one and this is the shortest one, well, the average would be somewhere in the middle, right? And so you could say, and again, if I clone this, oh, not that. I had the wrong item. So, and I'm almost done, and I'll shut up here in a minute because I know you're sleepy. I appreciate you all paying attention. Clone. So if you wanted to do the average cost or the average value, you would say, well, from 0 to 90 is the total. So then you would just say, well, this is going to be like 1/90th of the total, in essence, right? Is 1/90th of the total. Is that okay, JD? 1/90th of the total. We added this up. Some of the days are bigger, some of the days are smaller. You add them up, even those out, right? And you're taking a 1/90th of the total then, and that would be the average. And I think the book kind of glossed over this because they wrote it like this: 1 over 90 minus 0. And you can generalize that and say 1 over b minus a. Okay, would give you the average of anything, which is pretty powerful. Pretty powerful. Okay. And then last but not least, and this is the very last thing, I'm going to show you how you can check stuff on your calculator. We have the Riemann sum program, but we also can do integrals directly on the calculator. Actually, this would have worked. Maybe I should have just done that. Square root. No, maybe that wouldn't have worked. Let's just do one of the trig functions. I'm going to turn these off. Come on, I need one more. There you go. Okay, let's go. What mode are we in? We're in degree mode. Let's go in radian mode. A little easier to deal with. And let's go y equals like 4 sine x. Okay, this will be fine. And then let's go from, do our window from 0 to, let's see, sine goes down to pi, right? Let's go from 0 to, yeah, we should do a little extra. You're right. 0 to 4, not L4. Man, what a punk I am sometimes. X scale is 1, that's fine. Y scale, we can go from -1 to 5 should be fine because I did an amplitude of 4, and we should be fine then to graph that. Okay? There's the first little bit of sine function. Questions on that? It's okay? Now, bada bing, everybody. What if we wanted the area from 0 to pi here? Okay? We would go, this is brand new. You sleepy people, you're going to like this. Second, calc. Which one do you think it would be if we want to find the area under that curve? 7. Totally. Just hit 7. There it is. So you go integral, lower limit of integration. What did we say? 0, or Z if you're Canadian, A. Upper limit, second pi. Boom, there's your meditation. All right. And it says, and it quit at pi here. I did E instead of pi. Oh, man. So that's 2.718. I got to do it again. Thanks, Tyler and Julia, for catching that. 7, lower limit, enter. Upper limit, second. I did E, pi. That's better. And the area of that function then is 0.3446. So this is a good thing for you later on to be able to check things. We'll do these integrals obviously algebraically, and then you can check them with your calculator. So now we have the Riemann sum and we have this, both useful. I always do the Riemann sum so that you realize it's a bunch of little rectangles. Okay? Questions? Well, Hannah probably is in degree mode or something. What did I do wrong? 4 sine x. Let me. I'm in radian mode. Second calc. 7. Lower limit. 0. Upper limit. Pi. Did you do it over interesting. That makes more sense. It's all me then. Oh, you know what I bet I calculated was from E to pi or something like that. It's fine. It's fine. But anyway, this is a nice way to check your work. As always, I want you to do things algebraically and then to graph them to check. Okay? Questions? Preguntas? We got it under 20 minutes, which was my goal. So I'm going to sign off now. Thank you all.